another computer vision study group session. This time about masked autoencoders are scalable vision learners. So it's the name of the paper, quite long. But yeah, it's quite an interesting paper. It's written by the Facebook AI research team. There's some popular names on there, some well-known, like Kai-Ming He, of course, Ross Gershig, who was mainly involved in masked RCNN. Yeah. And well, I don't know about you, but in Germany today here it is quite a hot day. So I decided to actually give the whole presentation like a summer theme. So yeah, let's first start with a little intro, a little backstory, so to say. And we're here in ML City. So it was another day at the office in ML City for Huggy, right? You can see him sitting here or standing, or whatever he's doing at his desk in the office. And he just finished creating a nice new space and was ready for his lunch in the park. So he went out into the park. He was looking forward to a nice sandwich out on a sunny summer day. But he soon realized that it was getting way too hot. So let's say 38 degrees Celsius, that's quite hot, in Germany at least. I don't know what it is in Fahrenheit, but you can figure it out yourself, I guess. So it was so hot that he decided, you know what, I'm going to have a nice beach vacation. So he went and, he had heard about this nice place called Neural Network Island, where the machine learning folks go with their image pets to have a good time. And actually, about this image here, this Neural Network Island, I didn't paint it myself. Maybe you see it down here, the signature. It was painted by DALL-E 2. Because I was just looking for Neural Network Island and Google image search. It didn't really give me anything, and then I was like, okay, let's try DALL-E, and I really liked what it came up with. So that is Neural Network Island now, right? You've got trees, you've got neurons, connections, a lot of beach, and that's where Huggy is going now. So when he came to the beach, he was extremely disappointed, because it was just packed with images and he had no place. And he wondered why they were all hanging around at this one beach. And then he saw a sign. And the sign says, Google Vid training today. Bring your image for free TPU credits. Right, so you see Vid up here, observing all the images that people bring. Actually, it's all ImageNet images. And that's when Huggy knew, of course, they're giving away free TPU credits. And then all the machine learning people on vacation just brought their images to the beach to get their free TPU credits. But luckily, Huggy got a tip from a local about another nearby beach. And when he got there, he was quite relieved, because there were way less images. Just 6, really, here, right now. But something was strange about them, right? They look a bit strange, they look just fragmented. And then he saw a sign again, which reads, Fair My Training Today. So my, this is how I pronounce it, is like masked autoencoders, right? I will always say my, probably. And they advertise it with, bring your image for free Instagram followers, right? Because it's Facebook stuff. But of course, I mean, machine learning folks is way more interested in TPU credits than Instagram followers, so not as many people showed up as for the Google Vid training. But that was just fine for Huggy. And he even saw a booth that was offering free decoder classes. So he didn't know what it was, but he got some and put them on, and he was amazed. Because with the decoder classes, actually, he managed to see the images clearly. Amazing, right? So with his new decoder classes, Huggy spent a nice day at the beach. And in the afternoon, there was a classification competition between the vanilla vid, that's how we call the Google vid, the vanilla vid, and my, really. So Huggy was sure that my had no chance, because my just saw way less images. And it was a close result, but in the end, my surprised Huggy and even managed to outperform the vid. So my was a winner, right? And that is the first intro story that I had a lot of fun creating again. And now we can jump into the actual paper with some knowledge you already gained now. So again, that's the first page of the paper, right? I already said something. Oh, so it was released end of last year, actually. So it's not that old, or at least that version. Version 3 is from end of last year. Yeah. And what is it all about? These masked autoencoders. What are they doing there? And why can they perform image classification better on less images than vid, actually, right? And for that, let's first look at this vanilla vid from Google. So it was published in 2020 and was like the real first successful vision transformer. Probably most of you know it. And the biggest problem really at that point was that they needed a huge data set for good results. So to outperform convolutional and neural networks, they just needed a big data set. So they used like an internal 300 million something data set with which they managed to outperform it. But with smaller data sets, it just didn't work. And what are they actually doing? So they're just inspired by transformers for natural language processing, and they say, okay, let's create some tokens by actually chopping up our image into patches. And then we have, in this example, 9 patches. We feed them to linear projection layer, then we get some n-dimensional vector, and that's our token actually. So we put some positional embeddings in front, or just add them to them, and then we put them all into a transformer encoder. So the encoder looks just like this over here, right? You get your patches, you've got your layer norm, the multi-head attention, and a layer norm, then an MLP, and then you just stack a lot of these blocks actually. So there are different sizes of this vid, and in the end there's an MLP head that is using this classification token here and then can classify whatever is in the image. Okay, so that's the vanilla vid. Now the masked autoencoders. So first to say it's not really a new vision transformer model, but it's a framework for effectively training existing vid-like transformers. So you can basically plug in anything that is really like this vanilla vid. It has the same structure, and it works in a self-supervised way. So maybe you know Moco, or be it Dino or SimMim. They're all supervised frameworks, or self-supervised, not supervised, but self-supervised frameworks or methods to train vision transformers. But let's take a step back and look at autoencoders actually. So autoencoders are nothing new, right? Probably a lot of you have heard about them. Just a real quick intro to them so everyone knows. So the main structure in autoencoders really is that you have an encoder that takes as input an image, and then from that image it somehow creates a latent representation, and this latent representation is then again fed to a decoder, which then has the task to reconstruct the image from the beginning, right? That really just turn my image into some vectors and then try to unravel all of that again and get this image again that I put in. So it's good for self-supervised learning, right? Because you always have like a direct connection and you don't need any labels for the images. There's another class of autoencoders, it's called denoising autoencoders. And now there's some noise here in input image, and then the task is actually the same. Now it's just reduce the noise and create actually the original image. So you would actually compare the output to the original image and then have your loss between these two images. So that's autoencoders. It's nothing too fancy, I would say. Now let's look at the masked autoencoder architecture, where you also see like here's an encoder, right? And there's a decoder, and there's some stuff in between. There's an image that goes in and an image that comes out. Now the difference is that the image is in patches, like we saw in the vid example, right? We chop the input image up, and then we mask a lot of these patches, and we actually feed in the patches that are not masked, right? So the original patches, we feed them to the encoder comes up with some representation, some vectors, and then we add the mask tokens back in actually with the positional embedding, so at the right positions. And then we feed all of that, this whole masked and unmasked patches to the decoder, and the decoder then has a task to reconstruct all the patches and actually give us the target image. So the image that we first, or the original image without any masking that we put in. So that's like, really the basic idea of masked autoencoders. And how that actually works in more detail, we're gonna see now. So first we start with the masking, of course, where we create patches from an image. For example, here in our image we have 4 by 4 patches, so 16 patches in total, and we get the positional embeddings. Then we random shuffle all patches. I didn't visualize that because I was too lazy to chop it all up. And then they really just mask the last X% of patches, right? So they really just say like, okay, we've got our random shuffled list of patches now, or patch indices actually, and then we just take whatever percentage we want to use. And one surprising thing in this paper actually is that they say the higher the rate of masked patches, the better it works actually. So up to the point of 75% masked patches, which we can see here, for example. Okay, I will just repeat the question for the record, because I think your voice is not recorded. So the question is like, how different is this masked autoencoders to denoising autoencoders? And I had the same question actually, and in the paper they say like, it is like a subtype of denoising autoencoders we are using, but it differs in some aspects. But they don't really say in which aspects. They just say like, it's just different in some aspects. And maybe you could really see it like that. So it's like, denoising plus bird, and just the whole thing for images. So I think I'm not that familiar with denoising autoencoders in themselves, I have to say. So I don't know much about them. That's why it's a bit hard for me to like draw the direct comparison. But probably it's just really this advancement made with all the transformer structure and the patches, and then you have this bird-like training in a way. So I suppose that's probably the difference. Okay, then cool. And I will go on. Where was I? So they're really masking a lot of patches, and then they've got this masked image, for example, here. So you barely see just anything from the kite. So it's just really just a bit here, a bit there. There's some sky, and then they go and take these unmasked patches, so these 4 patches, and feed them in to the encoder. Then the encoder really basically is a vid. So they really just use a vid. Just any architecture, it could be a bit big, a bit large. They even use a bit huge. And this vid just produces the latent representation, right? So one thing they do is they add an extra layer normalization after the vid, right here. That is something, I don't know, that apparently was beneficial for them in their experiments, this extra layer normalization. But in the end, so in this example, you would feed your 4 patches and their positional embeddings to the vid, and you get out your 4 tokens, so your vectors or whatever you want to call them. And the next step already is the decoder. And for the decoder, as I said, we add in all the mask patches again, right? So it's basically just patches without any real information. But of course, they have to be trainable in a way. So I saw one implementation where it just used like a uniform random distribution and then just filled the patches with it. And they have the same size, of course, as the unmasked patches or the vectors from the unmasked patches. And they put it all in the right order, right, with position embeddings. They put it all like it should be. And then they put it in the decoder. And now we know the decoder is supposed to come up with the image again, right? Yeah, I think that's how you can see it, right? Yeah. Probably that's one of the main differences, really, to like autoencoders that just work with one image, right? Because here you have all these patches and tokens in the end, instead of this one big image that you try to do all as a whole. So probably that is one of the differences. So now we found one of the differences between a masked autoencoder and the denoising autoencoder. The representation in between. I mean, what's really great about autoencoders in general is that the encoder and decoder don't need to be the same architecture or anything, right? So the decoder can really be different. Of course, well, it still has like this vid-like block here, right? But it doesn't need to have the same amount of blocks or anything, and that's what they are experimenting with quite a bit in the paper. So they say, okay, if you just use way smaller decoders than the encoder, then we can just save a lot of time in computation and for the training, and we will later see like what the success rate there was. But in general, that's like a beneficial attribute of autoencoders, that this encoder and decoder are in a way decoupled. Just the decoder just needs to be able to really take in the output of the encoder. But what the decoder does after that is just up to the decoder, really. Okay. More questions here? No. Okay, so let's move on to reconstruction, actually, because now let's say, okay, we have our image here in the back. That's actually one of the real reconstruction images from the masked autoencoder, right? You see it is a bit blurry and everything, so it's just like, it's not ideal, but apparently good enough. And so let's see, now we've got our output here, we've got our original here, right? And for the reconstruction loss, we now only really look at the mask patches, actually. So we ignore the original patches completely, right? We really just take all these mask things and then we compare it, we calculate a mean squared error between these patches, and that's our loss basically for the training that we then use to optimize and get to our results. So it's really also interesting that they say like, it's way better when we really just look at the stuff that is completely made up, basically, right? Because these mask patches, it didn't really know anything about them. So the decoder had to do all the work in trying to figure out what it looks like. And you can see it's not really like fine structures it comes up with, right? It's more like these bigger areas. And I think, again, that's one point where transformers are useful, because like transformers are not looking at that much detail, especially the vid transformer. I mean, there are more fine-grained vision transformers that look at more details, but this vanilla vid is not looking at like details, but more at big areas for classification. And in this case, it's really helpful because, well, we don't have the fine-grained details from the reconstruction image. So how do we actually do the classification, right? So let's say you've trained your mask autoencoder now, and yeah, you've got your pipeline right here. So it's quite easy actually. You just throw away the decoder. So everything the decoder learned is then not important anymore. We just care about the encoder and how it learned the latent representation, and you put on a classification head like we saw actually in the original vanilla vid, and then you get your classification probabilities out. And yeah, the really good thing about it is that, for example, the implementation at Hugging Face, you can just train the mask autoencoder one, which is way faster than the vanilla vid one, and then you can use the weights of the mask autoencoder and plug them into the vanilla vid model, and it just works. So which is a great way when you have a lot of images that you want to train the vid on, or yeah, when you just want faster training, you can use the mask autoencoder and then yeah, use the vid model anyway to classify. Okay. Oh, you're a bit quiet. Yes, I can hear you. Now it's good now. Now it's good. Yeah, that's true. And I think one main difference to like, yeah, I could imagine that there's like this, maybe this pre-training with this jigsaw style, even for convolutional nets, but even in here we have the position embeddings, right, which are, I think, quite important actually, because we always know at which place in the image these patches are. And I think that's actually essential knowledge in this case, that it's not all shuffled around, but that we exactly know, okay, this patch should go here and this patch should go there. And yeah, so, well. But anyway, thank you for the... Yeah, I think what you're going for. Yeah, yeah. Yeah, that's true. Yeah, there's like this uncertain or this unknown, and you try to figure out, okay, this latent that works best to solve this, yeah, puzzle or riddle. I go on, and okay. So actually, so what's most amazing for me in this approach is really that you can mask like 75% of the image, and yeah, the mask autoencoder is able to come up with a reconstruction that is good enough for classification actually. So I wondered, okay, what's it like for us humans, right? So I took some of the images from their paper, and maybe you can all have a look. Like, okay, right here it's simple, right? We all know, it's really colorful. It's apparently some kind of bird with feathers, so that's parrots, right? So, yeah, it is parrots. And the next one might be a bit more difficult. So let's go from a human perspective, right? We see, oh yeah, there's some green here, so probably it's some forest or anything. It's a crown, and there's a cycle, and apparently some human. What's he doing there? I don't know. Maybe he's doing a wheelie or something. But so actually, it's a guy on a unicycle. Yeah, but still, I mean, we could see that it's like the forest and yeah, the crown and something with a cycle, right? So then I saw some black and white images actually, and I was like, that looks way more difficult. And I don't know if it's just for us humans or also for the machines, and that would be interesting. Actually, one of my questions to people from the paper would be like, did they experiment with the color schemes actually? Because I mean, for us humans, when it's black and white, we don't have these colors anymore to orientate ourselves, right? So we see a bit in here. So this structure, okay. Well, I already know now what it is. I don't know about you, but yeah, it is a steam train actually. So, but it's way harder to figure out when you don't have like a blue sky or green green trees or anything, at least for me. And the fourth example, that was some people like, okay, what if I would just see this stuff here? I would, okay, could be some clouds or something, could also be steam or whatever, and then maybe some ground, but this one here, yeah, so it is actually a guy on a skateboard and a half pipe. But when we look at the reconstruction, we also see, okay, it was a really hard example, and actually the autoencoder fails to reconstruct most of the upper body and everything, because yeah, there's just this huge patch missing here, right? So yeah, some examples work better and some worse, just as for us humans, I guess. Okay, what's the next one? Yeah, now we get to look at the performance, because they also reported some stuff about their performance, right? And well, they use two methods, linear probing and fine-tuning. Just probably, again, most people know, but just so everyone's on the same page. So linear probing is when you have your neural network, like you have a lot of layers, blah, 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 and you've got your output layer, and you just freeze the weights in these first layers, and you just basically have your fully connected last layer that you train. The rest just stays the same. And fine-tuning, or like a full fine-tuning, would be you just train the whole network again. And you can also do partial fine-tuning, right, where you just freeze some layers and you just leave some layers for training. For the fine-tuning or linear probing, I mean, linear probing is basically all except for this one, right? For fine-tuning, they're mostly doing full fine-tuning for the experiments. They have one figure where they say like, when we do just like partial fine-tuning, that's our results. But for most of the experiments, they really do the full fine-tuning actually. Yeah. So let's look at the performance first, right? So apparently, I already mentioned some other self-supervised methods like Dino, Moco, and Bait. So we see that with the different width size models, so it's big, large, huge, and then there's huge with a bigger image input image size. And we can see that, of course, the mask autoencoders are better than the rest, else I probably wouldn't really report it. Yeah, but we see it's not that far actually, especially for the bit big. It's 0.4 points better than Moco and Bait. And yeah, here you see the width performance without the supervised self-supervised training. So that's basically supervised and their own implementation. And they are using the ImageNet 1K dataset for their self-supervised experiments. And yeah, you can see that the best result is really with the biggest width model and the bigger image size. So here they're using 224, I think. So I think it's a half of what they then used here. And yeah, so in general, that's like compared to the other ones. And some more ablation studies they did was, for example, the mask sampling, right? So they are now using the random sampling. As I said, they're just randomly shuffling the indices and then just throw away or just decide which to mask from this randomly shuffled array, basically. But they also experimented with block masking, so where they just like do these huge blocks, and also with grid masking. But they are definitely saying, okay, best results are with random shuffling and random masking. Even though the grid is grid and also this block is not that far away, I would say, but still the random shuffling and masking is best. Yeah, and that's about the masking ratio. As I said, they are using something like 75%. So here in this axis you can see the masking ratio, and here you see the accuracy. Again, for fine-tuning first here. So for fine-tuning, you see there is a big step between 30 and 40. After 40, it's like, okay, it's about the same. So when you fine-tune the whole thing, apparently it's not that important if it's 40 or 75%. If you're doing linear probing, so if you're freezing most of the layers, then it is important, because then you see quite a steep curve actually. And then 75% was the sweet spot for them. That's why they just use it in the end. And the decoder size, as I said, the decoder can be of a size to be experimented with, right? And again, you see for the fine-tuning, the number of blocks in the decoder is actually not that important. You can even just use one block in the decoder when you do a whole fine-tuning and already get really good results. For the linear probing, again, it is important, or more important, because you get the best results when you have 8 blocks. That's why they use 8 blocks in the end in their implementation. In depth and in width, they have like 512 dimensional vectors that they decided to use. Again, for fine-tuning, it's often the case in the paper that for fine-tuning you are like, okay, well, you can also use small stuff, you can use big stuff, it doesn't make a big difference. It's mostly the linear probing that really got them to their parameters that they're using in the end. And augmentation, that's also interesting, because like data augmentation, so stuff like cropping the image, flipping the image, changing the color, right? It's color jittering. Is actually quite important for most self-supervised tasks. But here in the mask autoencoders, they actually say like, oh, it's not that important. Even if they use no augmentation, okay, it is worse than the rest. But especially the color jittering is actually degrading the score. So it's interesting, because this augmentation is really mostly one thing. We have to augment our images in self-supervised learning so it learns better. But here, probably because of this masking and this, already leaving out a lot of image information, it is not that important. Decoder size again. Okay, sorry. And they also did some experiments on object detection and segmentation with the COCO, right? So they were using like a RCNN, mask RCNN with baseline, and then they compared again with the other ones, and they were slightly better or on par with BAIT for object detection and segmentation on the COCO data. And for semantic segmentation, they used the ADE 20K semantic segmentation dataset with UberNet, and again, they were better than the rest. Okay. So you can also do that. And that's that for the paper itself. Thank you to this point. I do have some code you can look at, because the mask autoencoder is available in the Hugging Face transformers package, of course, and it's official implementation, which you can check out. I mean, the slides will be uploaded in the GitHub repository for community events later. And there's this Hugging Face vidmy, that's what it's called, so it's basically the vid mask autoencoder, right? And there's a really nice Keras.io example done by Arita and Sayak. And actually, when I had some questions from the paper, I often looked at this Keras.io example to just see how it could be implemented, what they're doing there, to understand some stuff. And I will quickly jump into this vidmy on Hugging Face. So that's basically the overview, right? There is some information here. You can see there's the vidmy config, where you can configure your whole stuff, whatever you need, like patch size, image size, number of channels, decoder, hidden size, decoder, intermediate size. Then there's the actual model, and then there's a vidmy for pre-training, which might be the most important if you want to really use it, because this vidmy for pre-training is the stuff that you can train your own images, can throw your own images for training, and then in the end get the weights that you can use with a normal vid. I will show you in a second. Niels made a notebook about it. And then there's the TensorFlow versions of it as well. I think also contributed by Arita and Sayak. Yeah, really nice. Let's quickly look at the notebook from Niels. Wait a second, here, this one. Yeah, that's the one. So you can see that here you get a feature extractor, right? Just the normal bit feature extractor is what you can use, and yeah, can use it from pre-trained Facebook with my base. That's a good model to play around with, actually, from the Facebook people. And yeah, then when you have your model like here, you can just create it. Well, here Niels mainly uses it to visualize the images or the masking and the reconstruction. And then here you can see, actually, so when you just really want to classify, you just load the for image classification from pre-trained, and you actually use the same model name. You can use any mask autoencoder model name that is trained with VID and just plug it into the VID for image classification class, and then you can go on and classify. Yeah, then there's a lot of warnings, actually. And Niels also says, like, yeah, because you're not using decoder weights, it will give you a lot of warnings. So don't be scared by that. And that's how it's supposed to be, apparently. And yes. Okay, to this point, are there any questions now? Yeah. Yeah. No, it's really just the mean squared error loss. They are doing a normalization on the pixels, but that's really all they're doing in like the original implementation. So from the reconstructed image, they're basically taking, yeah, they're normalizing the patches, and then they're really computing just the mean squared error loss between the reconstruction and the original. Yeah. Even though I saw in the official implementation, they also have a notebook somewhere. Let me just quickly spin it up. That they also have one checkpoint where they're using wait, GAN loss. It's called, I think. EMR with extra GAN loss. So maybe that's a bit the direction you mean. Yeah, I haven't looked into that, but you can see that reconstruction is better here, actually, than before, right? So they also have that, even though they don't report it in the paper, but in the official implementation you can find it. Okay. Okay. If there are no more questions, then yeah, no worries. It was a pleasure. And yeah, if you have any more questions, feel free to write me or write in the chat. I think the general event chat room in Discord, right? Yeah. So thank you for attending, and have a good day.